And I want to share my screen. And what I would like to go over is where we left off in our PowerPoint discussion last time. So last time we were talking about reactions and how specifically concentration changes can affect the reaction rate. So we know that all different kinds of things can affect rate. Can you name anything besides concentration? Anybody?
Temperature?
Yeah.
Pressure.
Yep. Anything else?
A catalyst?
A catalyst, absolutely. Is that all?
Surface area.
Surface area, is that it? Yeah, K, the reaction concept, but we're going to get to K and introduce that. We don't know what K is just yet. It's kind of abstract right now. The extensive answer for what affects rate of a reaction, well, it could be anything. Anything can affect it, and some things affect it more than others. We introduced 4 or 5 possible things, and we're going to go into detail of how the concentration of reactants can change the rate. But anything can, and it's possible. So what we do in chemistry is we mathematically model the effects of a few things on the rate, and we figure, hey, if you guys want to go off into a research institution and study something else, at least you'll have the basis for applying a mathematical model. So, you know there's an effect. We want to try to model that effect mathematically. What is the power of doing that? Well, the power is that you can not only show some effects on rate, but you can also predict what those effects will do to possible experiments in the future. So modeling is very powerful, and it's done in science all the time. And so that's what we're starting out with, our mathematical modeling. And so we talked about that last time, a little bit about all the effects, and then we were going to look at the concentration effect on reaction rate. We introduced some equations last time, like these ones, where you can say, oh, yeah, I kind of understand how the reaction rate can be affected by the change in the concentration of a reactant, in this case, with change in time. So we said, okay, yeah, that makes sense. And if we use an equation like this, then we would get units for rate in molarities per second. And that seems like a reasonable unit to quantify the rate of a reaction. A reasonable unit to quantify the rate of travel of a car is miles per hour, right? For a reaction, we're talking about molarities per second. That's reasonable. And so we introduced the equation, and we looked at some experimental, actually, we haven't looked at any experimental data yet. So then we went on to say that, well, shouldn't the rates of change of any one of the reactants or the products be connected to each other? So I have A and B as 2 reactants, and C and D as 2 products with their stoichiometric coefficients. And I know that as that reaction proceeds, as a reaction takes place, there are changes in the concentrations. And if I take the change in the concentration over time, like I did in this instance for A, then I can say, oh, well, geez, you know what that is? That's really just the rate of consumption of A in words. So I have the words that relate to the mathematical expression. And we define delta. Delta is just the change, and it's defined as a final minus some initial. And so that's how it's calculated mathematically. This is the expression mathematically, the way it's represented. And this is what it means in words. So you can read this overall rate equation in terms of those mathematical expressions or in terms of words. So what this says in terms of words is that the rate of a reaction, this rate of a reaction, can be found equal to the rate of consumption of A, that's this ratio, weighted or divided by the stoichiometric coefficient, small a. Or I could calculate the rate of reaction in terms of the rate of consumption of B. Of course, I need the stoichiometric coefficient here too. Or I can calculate the rate of the reaction in terms of the rate of production of C, and so forth for D. Any questions on that terminology and how it translates into words from the mathematical expressions? Okay, so we're good. All right, so we have this generalized equation here, and it would be nice now to apply that generalized equation and see why it kind of makes sense, you know, before we go ahead and look at other expressions. So what's done here in your notes is that we say, okay, let's take a look at this specific reaction of 2HI goes to H2 plus I2. Then if I apply this generalized rate equation and I apply this rate equation to this reaction, then I get these equations, which says that the rate of consumption of HI is related to the rate of production of H2, and it's also related to the rate of production of I2. Okay, now you guys, you have graduated from Chem 200, so you know what the stoichiometric coefficients mean in a chemical reaction. You know what these 2s and 1s here in front of the symbols for the compounds, what they mean. So I'm going to ask you a question, and hopefully we can refresh our memories of what those stoichiometric coefficients mean. Now, when I conduct this reaction, and I know that 2 moles of HI have reacted, that translates into how many moles of H2 produced?
That would be 1 mole.
Yeah, right. And you guys, you learned that from Chem 200, okay? So that's telling me that for every 2 moles of HI consumed, 1 mole of H2 is produced and 1 mole of I2 is produced. So out of those 3 components in this balanced chemical reaction, which one of those concentrations, HI, H2, or I2, which one is changing the fastest during this reaction?
HI?
Yeah, brilliant. Now, how did you figure that out? Because of your Chem 200. Your Chem 200 told you that 2 of those get used up for every one of the products that are produced. So that has to be changing faster. In fact, how much faster?
Twice as fast.
Bada bing, twice as fast.
Yeah.
So check.
Like
Yeah.
when I was studying this, it took me forever just to realize that, because I was like looking at the rate and I'm like, it says 1/2. Shouldn't that be a 2, not the other one? Wait, oh, it's the rate it's consumed because of that. Yeah, it took me forever just to understand. But yeah, I finally got it. Like,
You know,
if I hadn't studied this like with like an hour like before this class started, like I would be completely confused right now.
yeah, and I'm sure that there's some people out there that are. And so that's why I wanted to have this discussion, to show what's going on. Now, the rate of consumption of HI has to be twice as fast as the rate of production of these other guys, right? So this ratio here represents the rate of consumption of HI. So that number's got to be twice as fast. So I have to scale it by 2 or divide it by 2 so it equals the rate of production of the other ones. So it should kind of make sense now, this relationship and how they relate the rates of consumptions to the rates of production. And this is really the overall rate of the reaction by definition. It's defined this way. So it's defined that it will equal, the rate of the overall reaction will equal the rates of consumption or the rates of production of any of the other reactants or products that have a stoichiometric coefficient of 1. So if it's 1 here, then they equal the rates of production equals the overall rate. If it's not 1, then it has to be used as a scaling factor in this equation of identities. Now, just to help get this further cemented, I want to do a little recap of some Chem 200 and also go back to this idea. So I'm just going to put in a blank slide here, and I'm going to just make up a reaction for us to play around with. So combustion reactions seem to be easy. So let's do C2H6 plus O2. It's a combustion reaction from Chem 200. What are your products from a combustion reaction? Hydrocarbon plus oxygen gives
CO2 and water, right?
Yeah, good memory. Awesome. All right, so now we have to balance that using our Chem 200. And the way you do it in Chem 200 is just by inspection. So since oxygen's all together in this one compound, I'll leave that for last. I need 2 carbons here. So carbons are balanced. And I have 2 over here. So if I put a 3 here, then hydrogens, right, will be balanced. And then that gives me 4 oxygens, 7 oxygens over on this side, right? So I need to put 7 over 2 right there. Now, this is completely balanced mathematically, but chemists and physicists will argue that it's not right because if you take half of an oxygen, you get another molecule. It's a radical, so it's not oxygen at all. So you can't take halves. It changes the chemistry. So I have to multiply through by 2. So this was a 1, I change it to a 2. This was a 7/2, it gets changed to a 7. This gets changed to a 4, and this gets changed to a 6, and now it's balanced. Right? Everybody got that?
Yeah.
Okay, so that's a review from Chem 200, just balancing, like you know. And now I'm going to ask you a Chem 201 question. And you'll see this in your homework, maybe on an exam or something. Something like the rate of, what do you want to do? Product or reactant? Anybody?
Reactant.
Okay, the rate of consumption. It's hard for me to write clearly, sorry, on this consumption of C2H6 is 10 molarities per second, comma, what is the rate of production of water? All right. Now, before we go to answer this question, I just want to get a kind of a feel to see what you guys think. Out of all of these reactants and products, which one has the largest rate of change? Is it the ethane, C2H6? Is it the oxygen? Is it the carbon dioxide, or is it the water?
The oxygen.
Yeah, it would be the oxygen. Why?
It's the
It's
one
got
that's
the largest coefficient.
Yes, so it has the largest coefficient, so it's going to have the largest change, rate of change, because you need 7 of those oxygens for 2 of the ethanes, and it's only going to produce 4 carbon dioxide and 6 waters. So the water is got the second fastest rate of change, right? That makes sense. All right, so now I have the rate of consumption of the ethane, and I want to know what's the rate of production of water. So I can use that generalized rate equation on the previous slide to make the relationship and then calculate it. So first off, I'm going to do the relationship. So remember, we have that rate of the overall reaction, which they don't ask for in this problem. And I know that that equals 1/2 times the rate of change of C2H6 over time. And I can put a negative sign in there, indicating that it's a reactant. Now I'm going to relate that to the rate of change of water. And so they've given me this value as 10, and they ask for this one. So all I need to do is solve this equation for delta over delta T. That should equal minus 1/2 times. Now, since it's being consumed, this is they tell you it's 10 molarities per second, but you have to know that in the equation, in the math world, you got to put it in as minus 10 molarities per second because it's being consumed. And that's going to equal what I want.
Wait, but didn't you already put a minus sign in the negative 1/2?
Yeah, That's for the equation.
Uh,
Now, this is for the word. Because the rate of consumption, you're really losing that much, but nobody ever uses the negative. If you say consumption, then it's understood that this should be a negative. So it can get confusing. All right, so we got that equals 1/6 of what we want to find our answer. H2O over delta T. This is what we want. So I need that I see that I just need to bring that 6 over to this side to solve for the rate of production of the water. So that's going to equal -6 over 2 times a -10, which is 30 molarities per second. And so it's 3 times the rate of consumption of the ethane. And that's what our ratio said it should be. It's a 2-to-6 difference. Okay. Any questions on that? So one thing you could see here is that given this equation, if in a problem you are given any one of these quantities, whether it's the overall rate of the reaction or the rates of any one of the reactants being consumed, or any rate of production of any one, just one of the products, you can get all the other rates of the reactants or products or the overall rate of the reaction using this generalized rate equation. Pretty neat, huh? All right, so now we're done with that. Exercise, and we're going to move on to another related concept, which is called the rate law. Okay, the rate law. What we want to do in this section is we want to derive a mathematical formula that will tell us how the rate of a reaction should change with initial concentrations of the reactants. That's what a rate law is. So we use what's called the method of initial rates, which means in some reaction, let's say we're looking at this reaction right here of ammonium and nitrite. When you start a reaction in lab, you start with some concentration of reactants, and it's assumed that you don't start with any of the products. So initially, these are 0. And you have some values of the reactants. So what we're looking for is a mathematical equation that will allow us to calculate the rate given some initial concentration of reactants. Or we're going to find that rate law using the method of initial rates. Now, what is a rate law? A rate law is something, it's a mathematical equation that tells us how the rate of a chemical reaction should change when we change the initial concentrations of reactants. So as soon as I write down some reaction and I've identified what I'm calling reactants, I know what the form of this rate law is going to be. So I see this reaction, it has two reactants. So I know the rate is going to depend possibly on two things, this reactant concentration and this reactant concentration. So I know the rate's proportional to them, but I don't know just how it's affected by them yet. But I can write out a general rate equation, like this one down here. As soon as I know what the reaction under study is, I can write that the rate of that reaction equals some constant. Now that constant is going to be a constant as long as the only thing you consider a possibility for changing is the two concentrations or the concentrations of the reactants. If you fix everything else, and that means if you don't change the temperature, if you don't change the pressure, if you don't change the surface area, if you don't add a catalyst, et cetera, you don't do anything different except just change those concentrations, then this mathematical expression here should reflect those changes in concentration, which it explicitly shows in this position and in this position. Okay, we have some power dependencies here, but we don't know what they are. We know that this here is a constant. So how does that come about? You've seen this before. You've seen it before in Chem 200 with, for example, the ideal gas law. Remember, you went through all the different Boyle's law and the law of Gay-Lussac and Avogadro's law and all those other ones. And pretty much you show that pressure was proportional to the number of moles, the temperature, and inversely proportional to volume. And so you said, well, if I keep everything else fixed except these variables, then I can change that proportionality sign into an equal sign. And the proportionality constant was the ideal gas law constant, R. So you just put in a constant and it changes the proportionality to an equals. As long as you don't change anything except those variables at hand, this mathematical expression works. It's the same thing here. Here I have a rate that's proportional to the concentration of my reactant concentrations. And I want to change that to an equals, so I put in a proportionality constant, K. Boom. Okay, any questions on that? Any problems with that? So you've seen this kind of mathematical stuff before, and it's hidden in the scientific method, where part of the scientific method is when you want to understand the effect of something, then you only change that one thing and you leave everything else fixed in an experiment. And then if there's any changes that happen, it's due to that one thing. That's the scientific method. And so we can use that and say, if it's proportional to these things and I only change these things, fix everything else, then I can stick a constant in there and solve for that constant later. All right, no questions? Okay, so now, how do you find what those powers are here? These X's and the Y's. How do you find this concentration dependency so you'll know what the form of that mathematical equation is and how it affects rate, right? For example, let me insert another slide here. For example, I have rate is going to equal K times ammonium to the X and nitrite to the Y. How would the rate change, let's say, in another experiment, I'll call this rate 2, if I doubled the concentration of NH4 plus? Can I answer that question? How would that rate change in experiment 2 if I doubled the NH4 plus concentration? Can I answer the question? No, I can't answer it because I don't know what this is, X, right? If I did know, then I could tell you. All right, so let X equal, I don't know, what do you think? Let it equal 0. Start out with 0. Then this whole equation kind of reduces to this. Then if you double, let X equal 0 and NH4 plus 2 equals 2 times NH4 plus in experiment 1. So it's doubled. Then the rate in experiment 2 equals K times NO2 minus in 2, which equals K times NO2 minus in 1, because we didn't change the concentration of NO2 in 1 from 2. We left that fixed, right? We only changed one thing. So what happens to the rate when that happens? Anybody? The rate of 2 equals, whoops.
The rate of the NO2 minus?
Yeah, so it doesn't change. It's the same.
Yeah.
Yeah, so the rate 1, rate 2, that means if that power dependency X is a 0, then the rate of that chemical reaction is independent of the concentration of ammonium. It doesn't matter what you have. You could double it, triple it, half it. It doesn't change the rate, because if this factor is a 0, if X is a 0, it drops out of the equation, has no effect on rate. As long as I have some of ammonia in there, it's other than 0 amount, the rate is going to be independent of that concentration, and that reaction is going to just go along its merry way. Any questions on that?
So rate 2 would equal rate 1 here.
Yep. Yeah, so
Got it.
this equals rate 1. Thank you. Yep. But if X equals 1, and I do all that other stuff up here, I'm just going to put that right here so you see. So if I let X equals 1 and double the concentration and so forth, then what happens to rate 2? Let's see. Now this is 1. And this is in experiment 1 because it's double. It's double that. Sorry, right there. I need that coefficient. And I still have, I didn't change NO2 at all. I left that the same. So that's still going to be 1. So I could bring out this 2, bring it out to the front, K. Which equals 2 times rate 1. You see that? Anybody?
Yeah.
Yeah, kind of. That wasn't a confident, yeah. So there's 26 of you guys out there. Does everybody see where that's going? I only want to hear really from people who don't see it, I guess. Is there? So everybody's good with that. Wow, I
Yeah,
didn't
I'm
think I was
sorry.
that.
I'm like really lost. I have no idea even what's going on.
Thank you. Thank you for saying something.
Sorry, I'm just being honest. I'm like staring at it, trying to like go along with you, and I'm like, I don't know where all these numbers are even coming from.
Yeah, okay. So what I want to do then is go back a little bit and show you where these are coming from. All right. Now, we just introduced this thing called a rate law. And this rate law, it helps us track changes in rate with changes in concentration for any reaction. You write down that reaction, then I'll give you the form of the rate law. And that's what we talked about back here. So if I have a reaction A goes to B, then I know the form of the rate law here is going to be R equals K times the concentration of A to some power. That's the only reactant, so that's all I need for this rate law. For this reaction here, it had 2 reactants, so I needed 2 terms in this expression down here. Okay, so what we're trying to do is we're trying to get a feel for what this power means as far as its effect on the rate of a reaction.
Okay.
You know, what happens if I leave, everything fixed and only change that concentration? How will it affect the rate of the reaction? So I said, okay, let's take a look at some possibilities. One is if that stoichiometric coefficient X is 0. Well, if it's 0, then anything to the 0th power is 1. So this whole term right here, if it's 0, it drops out and I get, well, a 1.
Would that mean that there is no NH4 plus in the entire thing if it's 0 there?
No. That means the power of its effect is 0. It's called 0th order. That doesn't mean its concentration is 0. Thank you for asking that.
Oh, wait, so that means no matter how you change the concentration of it, then it won't make a difference.
Absolutely, that's it. You can have a thimble of it, or you can have a truckload of it. The reaction rate will be the same as long as you have some.
So we got the X, that's the stoichiometric coefficient for whatever the given reactions.
Okay, good. I'm glad that you said that. No, we haven't connected that to any stoichiometric coefficient.
Got it.
We're trying to first off understand how that equation works, the rate law. Then we're going to show you how to find that x.
Okay.
Okay, so you're a little ahead. All right, any other questions?
The part where I'm confused at is like you circle the X and then it goes down to NH4 and then all of a sudden you have 2.
Yeah, so the reason why I circled it is because
Yes.
I'm saying it's 0.
Hmm.
So this is 0.
Yeah, I got that part, like plug in X equals 0 and then off
So
to the side.
anything to the 0th power,
Mhm,
5 to the 0th power equals 1.
mhm.
So that's where this whole term then transfers into a 1.
Okay, now I got that. Thank you.
Awesome. Thanks for asking. All right, good. So we're good then so far. Okay. So we're trying to flesh out different possible effects on the rate and these mathematical equations. So I see if I put a 1 there instead of a 0 in our second example, then there's a 2 that comes up when I double the concentration from 1 in experiment 2. So now this equals, maybe I should have wrote this out. This equals the concentration NH4 plus in experiment 2. It's doubled that it was in 1. So I made that substitution and I just put in 2 times 1 so I can move that 2 out and relate what's left to rate 1. And now I can see that rate 2 would equal 2 times rate 1 if x was a 1. In other words, if this is x is a 1 up here, and this is first, that's said to be first order in ammonium because x is 1, that means that if I double the concentration of ammonium, the rate will double, just like I said here. And in fact, now you can see that if I tripled the concentration, if I change this to a 3, then this is going to change to a 3. So the rate would be tripled and quadrupled and so forth. If I quadrupled it, then it would be quadrupled. If I 1.5 times it, then the rate would go up 1.5 times. And that's called the first order effect of concentration on reaction rate. The 0th order effect is easy. It doesn't affect it. Okay, any questions on that now?
I think I got it.
Oh, that's awesome. Now I want to go to one more, second order. You guys ready? No, it's too much, too soon. All right, let's push on the second order because I think you're getting it, and hopefully this will work out too. So let x this time equal 2, and let's see what happens. So now I got rate 2 equals k. I'm going to double it again. So I'm going to put in 2 ammonium from 1, but this time it's going to go 2 up here, and I'm not going to change again the nitrite. So now this equals, well, 2 is in the brackets now to get squared. So this is going to equal 4. 2 squared is 4 K concentration of ammonium squared in 1 times the concentration of nitrite, whatever its dependence is, which we now see equals 4 times rate 1. Do you see how that works then? If it's a second order effect,
So the
that
rate would
how-
quadruple if it's second order and you double it basically.
yeah, if it's second order, if the concentration dependency on rate is 2, that exponent is 2, x equals 2, and you double the concentration, then the rate will go up by 4 times.
Mhm.
Now, if instead of doubling it, say I tripled it, so this becomes a 3 instead, right? How's the rate going to change? If this is a 3,
It would go up.
it would go up by how much? 3 squared.
So 9 times, yeah.
Yeah. Because it's in the parentheses with the 2. It's a second order effect. Okay, so I think you're just getting it. And this is kind of exciting because I think you need to just practice a little bit more with this idea. And you'll get the practice as we will see in the next few slides. Any questions so far on anything though?
I don't think so.
All righty then. Now, to get those exponents, those x's and y's in our rate law, remember the rate law is going to tell us how initial concentrations of reactants only affect the rate. That's what a rate law is. Now, you can't get those power dependencies, that x and y, by looking at the stoichiometric coefficients. Can't do it. They don't always relate. If they do, it's accidental. So what you need to do simply is to look at experiment. So you look at experimental data, and then from the experimental data, you determine the power dependencies of those concentration effects on rate, as well as that proportionality constant, K. You get it all experimental. And the way that your book explains this is pretty straightforward for easy cases. Now, what your textbook says is, first of all, you should only change one of the concentrations in a reaction at a time to see its effect. That's the scientific method, right? So you can only change one at a time. So if I want to find the effect of changing concentrations of ammonium, for example, and I'm going to use these experiments, there's 6 experiments that somebody did with different initial concentrations of the reactants, and they observed experimentally the rate. And they don't tell you how this was calculated. You just have to, take it that it was done correctly. When you get to lab, you're going to see how to calculate these rates of reactions, like Beer's law, for example. I don't know if you guys remember Beer's law's analysis from Chem 200. Essentially, what it is you shoot light at a sample of color. And as that color changes, that color change is related to the concentration change. So you can track the changes of concentration, and therefore you can calculate these rates using those equations that we already looked at, the change in concentration over time. And so that's how they were calculated, but it doesn't matter. right? Your textbook gives you these problems and it says, given these experimental data sets, tell me what the rate law is. And then it tells you how to analyze it. All right, now back to our analysis. We want to find the X, which corresponds to the effect of ammonium. So I'm going to pick two experiments that only change the concentration of ammonium and leave the concentration of nitrite constant. So it looks like the first two experiments. And I see that in the first experiment, the concentration was doubled compared to the second, or the second concentration was doubled, sorry. And the rate, look what happened to the rate. I doubled the concentration, rate doubled. Therefore, what? X equals
1.
1. Awesome, you guys. Because that's the way it should behave according to the mathematical equation we just looked at. If you double the concentration, the rate doubles, then it's first order. Done. And I'm going to pick reactions 5 and 6 to get Y, because I don't change the ammonium, but I double the nitrite concentration, and I see that the rate changes by 4 times. So what's Y?
2.
2. And so therefore, the rate law has this form. And it was obtained by analysis of experiment. Any questions on that?
I think I'm good.
All right. Now, see, this is a textbook problem. Well, sometimes you don't have textbooks. What if you get experimental data where in the experiment, they don't exactly double it, the concentration, right? And these guys aren't, you can't look at the rates and it's not 4 times, it's 4.875 times or something like that. Then what do? How do you analyze that? Well, what they don't tell you in the chemistry textbook is the way they explain this is a method you guys already know called solving a system of equations. So each one of these experiments gives an equation similar to this, except these are the unknowns. This is the unknown, and these guys are the knowns, this, and this. So all you need to solve a system of equations with 3 unknowns is 3 equations. And that'll solve all your unknowns. Now, you can do it like we just did in the textbook explains it when you have these type of examples. I call this the eyeball method. You just look at it, and from logic and analogy, from what we just studied about the rate law and how it affects the rate, then you can figure out the exponents X and Y in this case. But there's also a mathematical way to solve this. And if you do it the mathematical way, then you'll get it right every time. And you can use that mathematical check that I'm going to show you to check your eyeball method. And it's really simple. It's just a system of equations, but I'm going to skip through these 2 plates to get to it. It's not 2 plates, it's a bunch of plates.
Yes, sir. I have a question.
Yeah, go ahead.
So do the exponents always have to be whole numbers like 1, 2, 3, or could it be something like 1.5 or 2.25?
Okay, good question. Okay, so I won't skip these plates. Here, let's go back here. The fact is that those exponents can be any value, fractional and even negative. Did you get that? Hello?
Yeah, it's just like when all the examples I see in textbook, it's always that like very easy, straightforward double this, the exponent is 1 or 2. But I'm wondering if that
Zero.
reflects like reality. Is it like that most of the time, or
It's only like that in Chem 201. Okay, so having said that, these exponents can be negative or fractional, but in Chem 201, we just normally stick with 0, 1, or 2. Just to make it easy,
okay, I understand. Thanks.
right? Because the math, it just complicates the math, and who cares about the math? You know, if you want to be a mathematician, go down a few floors and you know, take more math classes. But see, we use math in chemistry to solve problems in chemistry. So you need to know how to work with math in order to solve chemical problems. But we usually just say, okay, we'll just do a couple math problems, and then anything after that is the same business. It's more of the same. Right, so it kind of gives you the idea of how to do it with some examples. And the examples we use in Chem 201 is 0, first or second order. Okay, but there's no reason why those coefficients couldn't be anything else. All right, now,
What about like S to the -1 and S -1 and stuff? Like, how does that work in?
okay, I'll tell you in a second. Now, you can have X and Y's that are negative, which means that as the concentration increases, the rate decreases. Like we were talking about the possibility of retardants to slow down reactions. So that's a possibility. Now, what you're talking about is the units of K. All right, so now we have this rate law for this specific reaction. And in fact, whenever we write down any reaction, we can get the form of the generalized rate law for that reaction by just looking at it. So this has one reactant, so our rate law is going to have one term, one possible term. Okay, so that's the form. This reaction has 2 reactants, so this is the possible form down here. All right, now, what is done is that this rate constant, which is the proportionality constant K, it's said to have units that change. And you've never run across anything like this. It's very rare to have some parameter where the units change depending on what situation it's in. So this K that's called the rate constant, its units depend on the overall reaction order. So for this specific example, the overall order, you sum up the orders. I have a first order here, a second order here. So the overall order is 1 plus 2, which is third. So it's third order overall.
Why do they change? Why does it change?
Okay, I'm going to get to that. Now they change because they have to make the rate of a reaction always has units of molarities per second or per time, but it's got to be molarities per time, usually seconds. And so the rate constant has to have units that change to make sure rate always has these molarities per second. So the rate constant depends on how many molarities you're putting in to this equation. If this is to the 1 power, it's 1 molarity. If it's to the 2nd power, then it's a molarity squared plus another molarity, it's a molarity cubed. So it's 3 molarities that you get here from the concentrations. So in this case, since one is 1 order, the other's 2, it's 3rd order, and those concentration dependencies are going to give me units of molarity to the 3rd. But my rate can only have molarities per second. So that means that the K that multiplies those has to get rid of 2 of them. And it has to give me a per second in there. So when the overall order is 3rd, the units are reciprocal molarity squared, reciprocal seconds. Do you see that?
Mm-hmm.
Anybody not see that?
So for the first order one, we can imagine that it's molarity to the 0 and seconds to the -1. It's kind of that pattern.
Yeah. Yeah. So
Okay.
so that's what it says right there, right? That's for first order. When it's just the overall first order, then you get 1 molarity coming from this term over here, not 3. And so that's good. And therefore you just need to multiply it by 1 over seconds to get rate in molarities per second. So this is the key. Rate has to always be in molarities per second. So K changes depending on the overall order.
What if it's 0th order? Then it just doesn't change it, so it doesn't matter.
Yeah, no, then K has has units that are appropriate for 0th order.
Mm-hmm.
Here, let me show you. So when it's 0th order, then what do the units have to be for K? To give units for this as molarities per second for the rate.
Molarities per second.
Yep.
Second.
Yeah, it has to for 0th order. And that's what it should say here if it had 0th order, but it doesn't. It just has first order, 2nd order, and 3rd. But yeah, you're right. For 0th order, then the units for K is molarities per second. All righty. I think this is something that we already talked about, so that's good. This is not really that important. This just shows the graphical behavior of concentration versus time, or the rate versus concentration for the different orders. So when you have the rate equals K times some concentration to some power, when this power here is 0, then the rate is independent of concentration. If this is 0, then this drops out, and the rate is a constant, and that's what you find for 0th order. The rate doesn't change with concentration. If it's the first order, then the rate is directly proportional to concentration. If it goes up by 2.2 in concentration, the rate goes up by 2.2 and so forth when it's first. And if it's second, then it has this kind of dependency where it lags a little bit behind first order until you get to 1 concentration, and then it goes up exponentially for second order. And so that's just kind of giving you a graphical feel for this equation. And now here is that thing I was alluding to before. You can find the rate laws by the eyeball method like we did if you have that textbook data. And even if you have it, you can check it by using the system of equations in math and just solving it, realizing that for any reaction, as soon as you write that reaction down, you have the form of the rate law. All you have to do is solve for K and X. And I can do that because if I have a whole bunch of reactions, then I can just put in these values for the concentrations and the rates and solve for the unknowns. And a way to do that is by just writing out each one and then dividing one by the other, having things that don't change, like the constant, or if you have other concentrations, they cancel out. If there's other concentrations here that don't change, they would cancel. And so you can use experimental data of rates and concentrations to calculate this exponent here, n, or what we're calling x. Okay. All right. I think we went through everything. Now we're ready to use that general equation there to solve a problem. And so that's what this next slide or two is about. Just using these generalized rate equations and applying them to the different experiments to find the orders or those power dependencies. So it's no big deal. I mean, you're reading through this and you're like, oh my God, what does this mean? What does this mean? Let me show you with an example what all that means. And then you'll be able to say, oh, it's not so bad. Okay. So let's go through what all that means with an example. All right, now we have a new reaction and I want to find the rate law of this reaction. Notice it's got one reactant. It's a unimolecular decomposition. Looks like it breaks into 2 parts. So you should be able to write the generalized rate law for this reaction. So see if you can do it if you got a piece of paper handy. So rate equals K times, finish it for this reaction. Are you finished? Okay, you should have had this CH3CHO to the X. Okay, so it's just one reactant and that's the form. So I need to find out what X is. Okay. And I have 4 experiments that are given to me to find out that. Now we know the eyeball method too, the one that your textbook. I'm going to show you, both and how that they agree. Look, experiment 1 and 2. What happened to the concentration?
It doubles.
Doubled. What does anyone see what happened to the rate?
Quadrupled.
Yeah, so what's the order?
2, second order.
Yep, times 2, therefore x equals 2. Now say it didn't come out this easy, so you can just look at it, right? Say it was it only went up by 1.5, and it was hard to see, how it was second order. How can I use that method of simultaneous equations to get the same answer? Easy. All I need to do is write down the corresponding rate law for each one. So I'll put that over here. So rate equals, and in this case, it's going to equal K times the concentration, 0.1. To X. And this is going to equal 0.02. The next one, K, equals 0.081. I'm sorry, not 0.08, that's the rate. 0.2. 0.2. I was trying to see if I could figure out how to mute people. Anyway, 0.2 equals 0.081, right? There are two equations from those two different data sets or experiments. Okay, so now I think you see, if I just divide one equation from the other, then this guy constant cancels out. And I get 0.1 over 0.2 to the x equals 0.02 over 0.08, which is around 0.25, right? So I got 0.5 to the x equals 0.25. So now I can solve for x. What does x have to be? 2. Just like we found using the eyeball method. So I just used those ratio of the two rate laws that were given to me for each experiment. Does everyone see that?
Yeah.
So you can use this ratio. I mean, every time you have an experiment, that gives you info, which you can use. All right, now that you know how to do that, we can talk about finding K, the value of the rate constant. Well, geez, I have all this experimental data, and I have the rate law now, because I know that this X up here is 2. So I can put in everything, the rate for experiment 1, I can put in the concentration in that 2 for experiment 1. The only thing I don't know is K, so I can solve for it. Right? So K in each one of these, once I know the rate law, should equal the rate divided by that concentration squared. And I can get it for each one of the experiments, 1 through 4, and then I can take the average. They should all be pretty much the same. Any questions on that? And so that's done for you, I believe.
Or when we looked at that one and solved it by inspection to begin with,
Yeah,
how much leeway can we give ourselves for saying that, 0.02 is equal to 0.081? Because I mean, that's close to 4, but
yeah,
not
that's
exactly
experimental
4, right?
error, right? Yeah, yeah. So I would say, within a percentage or so, within 5%.
All right.
Yeah. It's just round off error or experimental error. And that's what you see in these values. And you have to get used to that. Good question. All righty. So we got this next plate, which shows us what we just did. Also, it shows how to use one of the law of logs in order to calculate that exponent right here. So say you end up with an equation like this, right? I have my two rates, rate, and over here I have my concentrations to some power n. So that reduces to this equation. How am I going to solve for n? It's up here. A way to do that is to use one of the law of logs, which says that, well, it says this right here. The log of some number, let's say that number is x, to the y is equal to y times the log of that number x. And you can prove this to yourself if you don't believe this law. Just put in numbers like the log of 2 to the 3 equals 3 times the log of 2. So in your calculator, take the log of 2, then times it by 3, and see that that number equals the log of 2 cubed. And you should get the same thing. So this is a law of logs. And this could help you solve equations like that. So in other words, I take the log of this side and I equate the log of this side to n times the log of 0.666. So the log of 0.445 equals n times the log of 0.6666. And so I can solve for this explicitly by taking the ratio, and I find out what n is, which is what we found from the eyeball method too. So that's an application of the law of logs that may come in handy in other spots in your career. Any questions on that?
No.
All right. Now, so we were talking about solving for K a while ago and plugging it in. So for this example, you can do that. And the answer's here. I just turned it upside down. So you can check it. So try to work that out. So it should be the same for each one. You could take the average if they're a little different, but you would solve for it like we were talking about back here for K. So you're going to practice those for next time, I guess.
For those blank spaces, is it 2 and then second order?
What blank spaces?
On the slide where we have the upside down answer.
Oh. Yeah, so here we just solved for K. So if I go back here, for example, and I solve for K, I can take one of my rates right here, 0.02, and I divide that by the concentration that corresponds to that rate, which is 0.1, and it's second order, so it's squared. So if I put that in my calculator, I have to grab my calculator. I should get 2, right? 0.02 divided by 0.1 squared equals 2. So K equals 2. 2.0. To the right number of sig figs, because this has 2 sig figs and so does this. And that's what's shown here.
Right, so if we were gonna fill in those blanks, the rate goes up by 4 then. And then
Yeah,
on the slide you were just on,
yeah, it goes up by 4 from here to here. Right?
okay.
Okay. Any other questions? Okay, so we're a little bit over time there here. Sorry about that. I was hopefully going to get to integrated rate laws, which will help you prepare your report for lab, but we're going to have to wait until Monday to do that. So thanks for your attention, and I'm going to wait till everybody's gone.